A very good morning to Dr. Fatima. We are UMT Computational Mathematics students who take the subject Mathematical Methods this semester. I am Choon Yi.
I am Choon Wei.
I am Lim Kim Man.
I am Lim Seng Wei. Today, we would like to explain our coding in Mapper and discuss the result for our project about heat conduction through a metal bar.
First, we look at the question 1C Roman 1. In this question, we are going to evaluate Bn. By referring to the chapter 3 in the lecture note with about 40 series, since the function ust we get in question 1b is only left the same term. So we can evaluate Bn by using the following sine series with this formula. From the question, it's given that Fs is equal to F and L equal to 1. So we substitute into the Bn formula and we do the integration by mapper and we get this. Assume that n is an integer. We know that cos n pi is equal to -1 power n and sin n pi is equal to 0. Then we can simplify Bn into this form. Next, for the question 1C Roman 2, we need to determine the first 5 coefficients in the series. To get the first 5 coefficients in the series, we need to substitute the value of n from 1 to 5 into the Bn formula that we obtained in question 1C Roman 1 with this formula. So by using mapper, the first 5 coefficients in the series are this. Next, for the question 1C Roman 3, we need to sum the first 5 terms in the series and given that k equal to 1. By using mapper, the sum of the first 5 terms in the series is this equation. After that, we need to plot the sum for t equal to 0 to t equal to 1 with step size of 0.2, and we get this graph. Next, for the question 1C Roman 4, we need to vary k. Since the diffusivity of the metal bar is denoted by k is a positive number, so we can investigate the behavior of the metal bar temperature to plot our function ust for s from 0 to L by setting k less than 1 and k more than 1. For k equal to 1, we get this graph. For k equal to 0.001, we get this graph. And for k equal to 5, we get this graph. Okay, so now look at the PowerPoint. When t equal to 0, the temperature for these 3 graphs are almost the same. You can see that they are almost the same, look like this shape. Okay, so we use maximum temperatures as a representation because we must consider the maximum temperature of the metal bar. For the behavior of the metal bar temperature, by varying the value of k from lower to higher, we found that the time taken for the maximum temperature of metal bar drop to 0 is become shorter. You can see this space. For k equal to 5, the white space is small, and k equal to 1, the white space is bigger. Besides that, this behavior also applies to other temperature. It's the same only. Okay, so we should use the material with higher diffusivity, K, so that the temperature of the metal bar will drop rapidly in the shorter time.
Next, for the equation 1C Roman 5, and this one, we need to repeat the step from C Roman 1 to C Roman 4 with the given Fs, which is Fs equal to S for S from 0 to 5 and Fs equal to 1 minus S for S from 0.5 to 1. So first, we need to calculate Bn using the Fourier series method. Bn is this formula. given that L equal to 1. So we substitute into Bn formula and we do the integration by method and we get this formula. Next, we will substitute n from 1 to 5 into Bn formula to determine the first 5 coefficients in the series. So by using mapper, the first 5 coefficients in the series are these ones. Next, we need to sum up the first 5 terms in the series, and given that k equal to 1, by using mapper, the sum of the first 5 terms in the series is in these equations. So after that, we need to plot the sum t equal to 0 to t equal to 1 with step size of 0.2 and we get this graph. Next, we need to varying k. Since the diffusivity of the metal bar which denoted by k is a positive number, so we can investigate the behavior of the metal bar temperature through plot the function ust for s from 0 to L by setting k less than 1 and k more than 1. For k equal to 1, we get this graph. For k equal to 0.001, we get this graph. And from k equal to 5, we get this graph. When t equals 0, the temperature for these three graphs are almost the same. We use the maximum temperature as a representation because we must consider the maximum temperature of the metal bar for the behavior of the metal bar temperature by varying the value of K from lower to higher. We found that the time taken for maximum temperature for metal bar drop to 0 is become shorter. Besides that, this behavior also apply to other temperature. So we should use the method with higher diffusivity K so the temperature of the metal bar will drop rapidly in the shorter times. In general, the temperature of graph 1C Roman 3 is higher than the temperature in graph 1C Roman 5. For T equal to 0, the maximum temperature of the graph 1C Roman 3 is 1. When the S is between 0.8 to 0.9, while the maximum temperature of the graph 1C Roman 5 is 0.23 when S is 0.5. Observe that the graph for 1C Roman 3 and 1C Roman 5 for T larger than 0, the temperature diminishes steadily as heat is metal bar is lost through the endpoint.
For question 2b, we need to evaluate Bn first. By using the Fourier sine series, Bn is this formula. Given that fx is equal to x and L is equal to 1, so we substitute into the Bn formula and we do the integration by method and we get this. Next, we substitute the value of n from 1 to 5 into the Bn formula to determine the first 5 coefficients in the series. So by using method, the first 5 coefficients in the series are these. Next, we need to do the sum of the first 5 terms in the series and given that k is equal to 1. By using method, the sum of the first 5 terms in the series is this equation. After that, we need to plot the sum for t is equal to 0 to t is equal to 1 with step size of 0.2 and we get this graph. Next, we need to varying k. Since the diffusivity of the metal bar which denoted by k is positive, so we can investigate the behavior of the metal bar temperature through plots of function uxt for x from 0 to L by setting k less than 1 and k more than 1. For k equal to 1, we get this graph. For k is equal to 0.001, we get this graph. And for k is equal to 5, we get this graph. When t is equal to 0, the temperature for these three graphs are almost the same. We use maximum temperature as a representative because we must consider the maximum temperature of the metal bar. For the behavior of the metal bar temperature, by varying the value of K from lower to higher, we found that the time taken for the maximum temperature of metal bar drops to 0 is become shorter. Besides that, this behavior also applies to other temperature. So we should use the material with high diffusivity, which is denoted by K, so that the temperature of the metal bar will drop rapidly in the shorter time. Next, we need to repeat the steps from C Roman 1 to C Roman 4 with the given fx, which is fx equal to x for x from 0 to 0.5, and fx equal to 1 minus x for x from 0.5 to 1. First, we need to evaluate Bn. By using the Fourier sine series, Bn is this formula. Given that L is equal to 1, so we substitute into the Bn formula and we do the integration by mapper and we get this. Next, we substitute the value of n from 1 to 5 into the Bn formula to determine the first 5 coefficients in the series. So by using mapper, the first 5 coefficients in the series are these. After that, we need to plot the sum for t equal to 0 to t equal to 1 with step size of 0.2. And finally, we get this graph. Next, we need to vary in K. Since the diffusivity of a metal bar, which denoted by K, is a positive number, so we can investigate the behavior of the metal bar temperature through plots of function uxt for x from 0 to L by setting K less than 1 and K more than 1. For K equal to 1, we get this graph. For K equal to 0.001, we get this graph. And for K equal to 5, we get this graph. When T equal to 0, the temperature of these three graphs are almost the same. We use maximum temperature as a representation because we must consider the maximum temperature of the metal bar. For the behavior of the metal bar temperature, by varying the values of K from lower to higher, we found that the time taken for the maximum temperature of the metal bar drops to 0 becomes shorter. Besides that, this behavior also applies to other temperatures. So we should use the material with higher diffusivity, which is denoted by K, so that the temperature of the metal bar will drop rapidly in the shorter time. In general, the temperature of graph 2b Roman 3 is higher than the temperature of graph 2b Roman 5. For T equal to 0, the maximum temperature of graph 2b Roman 3 is 1 when x is equal to 1, while the maximum temperature of the graph 2b Roman 5 is 0.23 when x is around 0.5. Observe that graph for 2b Roman 3 and 2b Roman 5, for T greater than 0, the temperature diminishes steadily as heat in the metal bar is lost through the endpoint. So that's all from us. Thank you for watching.